Hi, everyone. Welcome to my talk on evaluating large language models and embeddings in production. I'm Amber Roberts, an ML growth lead at Arize, and let's get started. So I don't really need to talk about the change that's been happening in the last 12 months, all the advancements in generative AI. But as we've seen week over week, month over month, things are changing at a pretty crazy rate. And we're just seeing more and more applications for large language models in production, as well as capabilities of generative AI. And what we're also seeing are the areas that they're affecting. Not only are generative AI models being implemented in a variety of different use cases and different industries, but now there's research being done into what kind of jobs will be automated through this, and then what kind of roles will change to accommodate this new technology. And as someone who's been a machine learning engineer and works with a lot of machine learning engineers, I've kind of thought about the space and seen how machine learning engineers are leveraging large language models. And they're still having to do a lot of the implementation for AI, but now it's more encompassed in leveraging tools to deploy, monitor, and maintain these models in production. So you still need to be able to build these models, but building is starting to look a bit differently, especially with LLM workflows, and we'll get into that later. But you need to be able to look at performance, drift, bias in every one of these models that you implement in production. And that doesn't just go for one model, it goes for all the features, all the embeddings, the model versions, and even the type of model that you're monitoring. And it used to be folks were kind of looking at the differences between monitoring and observability. But now folks are interested in LLM observability as well, so the observability of these large language models. But the main parts still stand. Monitoring is that tip of the iceberg. It's the first step to understanding how your models are doing in production, whether it's a traditional ML model or one of these LLM models. The observability part is that root cause analysis and being able to resolve these model failure modes. For how LLMs look like today in production, we're seeing a lot of chatbot capabilities, a lot of personal assistance. So if you were to send a query to an LLM, you might be going through an agent, through a framework, through some kind of assistance, maybe a prompt template, and then you are getting a response based on the query you initially made. Now, it could be more detailed, it could be altered, and you can even add information to it through prompt engineering. But this is a general, typical workflow for something like a chatbot or a user that's using an application and trying to get a better understanding of what's going on through a chatbot. And as we talk to more and more companies trying to implement large language models into their own workflows, we're seeing a hesitancy, and it's completely understandable. From those we've surveyed, 46% say that they are worried about inaccuracies. And these inaccuracies could come in the form of hallucinations, inaccurate responses, bad prompts. And we've seen these happen. We know that they do happen. The key isn't just saying we're going to prevent these entirely, but that we're going to be able to figure out exactly when these models are hallucinating, catch it before that information gets back to the user, and fix it. We want these done as fast as possible because time to value is what's really going to matter in the long run, not just about deploying these, but maintaining them and making sure that they're giving the best answers as possible to reduce churn and increase customer satisfaction. We've seen that teams say when there's an issue in their ML flows that it takes at least a week. 84% say at least a week to detect and fix these issues. And then 12% say at least a month to detect and fix these issues. So we want to be able to find those errors even before they get back to the users if you're using an LLM. So being able to troubleshoot and really improve that time to value, find those errors and find where those errors are occurring in order to fix them. And just a few quotes from those surveyed. We've really seen that the amount of time and money that's put into AI in production and teams, it's difficult to understand that value add because a lot of times these unstructured models in particular, it's hard to evaluate them. So making sure you have ways of figuring out the return of investment you're getting on these models, how much time you're spending debugging them and correcting them is really important to making a team as efficient as possible and making sure your models are giving you that AI ROI. And so observability is still around ML, but now we're seeing an ML ops type tool chain where new tech is now powering LLM observability. So prompts, prompt management, agents, evaluations are all now catered towards LLM observability for those wanting to implement kind of the latest in generative AI into their system to essentially increase productivity and profitability for that company. The emerging LLM toolchain that we're seeing are focused around third-party LLM. So essentially you're starting with the source model, and then you're using some kind of vector database or LLM memory storing techniques, storing embeddings, storing queries, and then using maybe an LLM app or some type of framework like Llama Index or LangChain. And then at the very end, thinking about observability. It's not enough just to implement this tool chain. You need to make sure that it's working continuously and you are consistently able to solve the problems that arise once you put that model into production. Now, this is essentially the full tool chain, the big picture, but just diving into actually monitoring for unstructured use cases and then LLMs, we first need to just think about unstructured data and what makes it so difficult to deal with in the first place. We know over 80% of the data collected is in an unstructured format. So data, audio, data that's audio or visual or videos. And a majority of this data isn't used. Around 90% of the data collected is kind of just sitting in a data warehouse or database and isn't being leveraged for that personalization aspect that a lot of companies want to leverage it for. And part of the reason why is unstructured data, it's hard gaining insights into it. These also tend to be large data files, right? So we need to figure out a way to monitor unstructured data in a manner that makes it scalable and accessible. And just going back to some of the difficulties, when you're trying to make it accessible and scalable, you're doing so in trying to gain visibility into the data. If you don't have visibility into how that data is actually moving, there's no way to troubleshoot it. So we need to essentially visualize it and understand that data that's kind of in this high dimensional space and make it to a point that you can interpret it and understand where it's failing. And we do these through embeddings. Embeddings are essentially the backbone that's powering this generative AI movement, powering large language models, and can be seen in a variety of use cases that are focused around generative AI, whether that's language or vision. And for those not familiar with embeddings, they're vectors that encode semantic meaning. So a distance encodes a given understanding to the data. So if you have vectors like, let's say we can represent man in this high dimensional vector, represent woman in this high dimensional vector, and then we do a dimensionality reduction technique, we can then see semantic relationships. So man is to woman as king is to queen. You can also think about, if I want to convey to technology, how do I represent a color? Like, I'm not just going to say, oh, I want my website to be blue or pink. You need to be able to use a vector to represent that color. So if you think of a color cube, you can give a three-dimensional coordinate and it would find its place in this cube and correspond to an actual color. In terms of the embedding projection that I mentioned, sometimes you have a three-dimensional cube, but a lot of times you have an in dimensions. So vectors that are in a very high dimensional space, sometimes these are thousands of dimensions. And what a dimensionality reduction technique would we'll do is project it into a lower dimension, either 2 or 3 dimensions, so we can interpret the findings. And as long as the key information is conserved when we're doing that dimension reduction technique, we are able to interpret what's going on in those high dimensions. So when choosing the technique to use, you really want to preserve local and global structure. So when we're looking at Mario in 3D versus 2D, we're seeing the structure is overall preserved. It's not looking, Mario's not going from 3 to 2 dimensions and looking completely different. So that's essentially what we want. We want to know in this high dimensional space what close things are actually close together, what far away things are actually far apart, so we can look at it globally and locally. And how Arize does this is through a custom UMAP, or uniform manifold approximation and projection. And this technique is really great for preserving that local and global structure. If you have more questions on that, I'm happy to answer them through the Arize community Slack. But it's great with nonlinear data. It is a form of a neighbor graph, and it's fast in comparison. These are computationally dense. It does depend on what you're running, how fast the rendering will be, but it is very robust to parameters. So you can change out a few parameters and you're essentially going to get the same structure. Now that's important because I mentioned, if we take 3-dimensional Mario and put it in 2 dimensions and we play with different parameters, we still want the Mario character. We don't want it to look like something completely different because we care about preserving information as much as possible. You're always going to lose information as you decrease the dimensionality, but you don't have to lose the most important information that you can then interpret. And I'll get into what I mean by that in a moment. A key thing here is, so you're now seeing like clusters of data. So this UMAP example here is just one point in time. So this could be like one data set at one point in time, and then you can continue to compare projections over time. So if you have clusters that move, maybe you look at, where the data for your embeddings was last week compared to this week, what's changing, maybe a whole new cluster emerged in production and it's not really seen in the training data. You need to see what is drifting. So you can use drift. We're going to get into performance in a bit, but drift is the fastest way to see how things are moving. If you're continuously doing your dimensionality reduction techniques, you can see how the global data set's moving, and you can see how individual clusters are also starting to move. These can be measured through magnitude measurements like cosine, or distance measurements like Euclidean distance. You can also even see how much of one local cluster is part of another cluster in terms of data. So how much of that cluster is from production versus training. So you can understand the balance of data with those clusters. Because a lot of times we see issues happening in production have to do with a class imbalance or a data imbalance. And so making sure that data is in the training is really key to making sure unstructured models are performing well in production. You really want balanced data, and you want it essentially across all areas that you're seeing in production. And as the use cases grow, so are the techniques. So that's just one technique, drift monitoring for embeddings, that you can use to track how well any model that leverages embeddings or unstructured data is doing. Another example are prompt and responses. So you can think of prompt and response pairs as embeddings. You can take any text, maybe you want to save all the prompt text as an embedding. Maybe you want to save the response text as an embedding. Maybe you want to add them together and make that an embedding. Essentially, you can make any text combination an embedding. And if we do that, let's say we have prompt and response pairs, we can generate those embeddings, we can do dimensionality reduction techniques, and we can generate these clusters. So data will cluster, and maybe these are, cluster 1, responses in Spanish, cluster 2, maybe these are impolite responses, and cluster 3, inaccurate responses. So you can understand what's going on in the clusters, even just by clicking into the cluster and seeing the data that's held there. But the next step forward is really about evaluation. You want to be able to see how well your model is actually doing at responding to these prompts, right? And you can do that by generating a metric that goes with that use case. So if you have a prompt and response, maybe OpenAI's evals, and then you can get a selected metric set of, these metrics can be used to evaluate performance on that model. And there are a few different ways evaluation can look for large language models. Probably the most common and traditional way we've seen has been user-provided feedback. This happens a lot for personalized recommendations. Like if you're asked to give a how many star rating for items you've purchased on Amazon or movies you've watched on Netflix, or maybe just a thumbs up, thumbs down, like how did we do on that response? And then task-based metrics. So whether it's something like a traditional metric like accuracy or recall, or if it's a task-based metric like using Blue Score or Rouge Score, or the OpenAI evals for LLMs. And again, like more and more metrics every day are coming out around monitoring and performance for large language models. But as you can see here, there's user-provided feedback, task-based metrics, and then the new area that's really taking off and pretty much the direction we're going as these use cases get more and more complex, you're going to want an LLM assisted evaluation. So an LLM to actually evaluate how well another LLM is doing. And just to show you what this looks like, how an LLM assisted evaluation would work, you have a series of prompts and responses, and they can go into an evaluation system. And then you can have some task-based prompt template that gives you an understanding of the prompt template, like how it's laid out. And essentially you can use an evaluation LLM to produce scores. And this is where the monitoring comes in. Maybe you say you need an evaluation score of at least 6 to be in the clear. Anything below 6, you want to be alerted, because that's not enough of a confidence that you can just give that answer to a user. So then all the alerted responses for those prompts are run through a secondary LLM and gives you a suggested improvement for your workflow. And this is how you can catch a lot of just first round errors in a prompt and response system. For an LLM improvement workflow, there's several types of workflows that can be used to essentially fix the problems that we were talking about earlier, hallucinations, just overall bad responses or inaccurate responses. And you can do that by either asking better questions or trying to get the LLM to give you better answers. So the way that looks is in prompt engineering. All right, we're going to do some prompt engineering, work on the prompt template, generate better prompts, or maybe give it more context. And we see this a lot in search and retrieval cases or RAG cases, where essentially you're storing the data in a vector database, you're given a prompt from a user, and you're trying to add additional information to that prompt. So the LLM can see that information that you're giving it and produce a better response. So essentially adding contextual information. So adding as much context to the query as possible before the response is generated by the LLM. And then also just training your LLM, doing fine tuning on your LLM. These obviously can be complicated if it's a non-open source LLM, but there are fine-tuning techniques that have been showing up more and more, and it is a possible option for figuring out and improving your LLM workflows. So for prompt engineering, essentially having a set of prompt templates, and you can see essentially like you have input data, instructions, given context, and then you're giving an approval rating. And essentially here you're given an evaluation metric. So, you're surveying people, like how many people approve of the response you're giving out here. And you can use this to essentially choose, maybe you're choosing between prompt templates, or maybe, you're putting this into a secondary workflow. For troubleshooting a bad retrieval, so essentially you're looking at how things are looking over time. I also recommend testing out the Arize platform. There'll be a QR code at the end that you can scan. So you can actually see how a query versus context ratio is set up. But essentially, anytime you're getting an alert, focus in on that alert, figure out the mix match that you might be seeing between query and context, like where do you need to add more context, and then go back and actually add that context. Like user wants more video docs because there's not more context. So you add additional information into that vector store in hopes of getting a better response to the query. So all this is the context that you're adding for the query. And essentially, this is because you found a gap in the data, a gap that's not giving you a great response. And so the more context, the better. You've probably seen this if you played around with ChatGPT, and if it didn't give you a great answer to your query at the beginning, you gave it more information to then improve the query. And then fine tuning for LLMs. Step 1, 2, and 3, essentially you find the problems, pinpoint the similar points, and then you can export it to actually fine tune and get really kind of individualized ideal responses. So this is good for very specific use cases. I will say that from what we've seen, you might want to start with either prompt engineering or adding context before going into fine-tuning the LLMs. Research has been done to show that it will give you the fastest and largest bump for the lowest amount of effort when improving your responses. But this option would be great if you have a very particular use case that you need ideal performance on. And so these are now offered by Arize. Arize has put out, as you've seen in the past, ranking, regression, more traditional ML, CV, NLP, classification, having observability around there. But now we're also offering LLM observability. So tasks, prompts, and things that can really go into making sure LLMs are working as well as possible in production. I just wanted to mention Phoenix, which is Arize's open source offering, where you're able to, and you can even see from the GIF here, be able to dive into individual clusters of these embeddings and troubleshoot them. So there's a lot of ways to visualize, understand, and see the data at hand. And we're doing a lot of workshops around Phoenix. So if you're looking for an open source option to monitor your embeddings and to kind of put monitoring in place for the large language models that you've been kind of experimenting with and testing out for your use case, I'd highly recommend checking out Phoenix. If you have any questions, I'm amber@arize.com. I'll also be available in the Arize community chat, and you can sign up for free for the Arize account. You can, clone the Phoenix repo. And we also have a whole host of events and certifications that are available for free on the Arize site. Thank you.